This is going to be a mini lecture here over the problems out of chapter 2. I'm going to go through these one by one so that you can kind of get a flavor for what's to be expected of you. We're going to look at problem 1 to start. Use the standard prefixes listed in table 2.2 to express all of these. Now, if you go to table 2.2, you can see all of these symbols here. This is what you're going to end up using. So if we were to go here, if I can get to it, which apparently I'm having some issues with, there we go. Okay, so 10 to the 6th phones. What we need to do is we need to go here and we need to find something that is 10 to the 6th, which if I can find a way to magnify this a little bit. That's not the option. Huh, seems to be going in the opposite direction I want. You can see it here. This refers to mega or 10 to the 6th. So if you have 1 megahertz, basically you have 10 to the 6th hertz. So if we abandon that and go here, we can then say 10 to the 6 phones is the same as saying 1 megaphone. If we look at 10 to the minus 6, again, if we go back, we can look at 10 to the minus 6 here is micro, which has this mu, Greek letter mu, that goes along with it. So that means here we end up with 1 microphone. Not much to all of these except going through and trying to figure this out. This one is 2 times 10 to the 3rd, 2 times 10 to the 3rd. If you go back and you look it up, you'll find out that is kilo. So you could have 2 kilo mockingbirds. So whatever it is you have a unit of, there is whatever you will attach to the prefix. So that's how number 1 goes along. Number 2 here, how many milliseconds is a 1/10 of a second radiographic exposure equivalent? Well, we know that the milliseconds, if we go here, again, look at the table, milli refers to 10 to the 3rd seconds. So if we go here, we can see here that 0.1, if we were to take this and translate it, or 1/10 becomes 0.1 seconds. How many milliseconds is that? Well, we know we have 0.1 seconds. There are 1 second. This is the unit that we want to get rid of. This comes out of dimensional analysis. If you're looking to get rid of a unit and replace it with another, then you have to multiply by a conversion factor. And the conversion factor here, we know there are 10 to the 3rd milliseconds in 1 second. This is the same thing as saying 1,000. So we know that and that cancel. We have essentially 0.1 times 1,000 So we should end up with 100 milliseconds. Now, am I correct? Is this, let's go here. Let's check the answers. Make sure I'm not misleading you. And indeed, that's the case. Okay, so far so good. All right, so now let's go to number 3. How fast does a 1 kilogram object have to move to have a kinetic energy of 1 joule? Well, this was something that you can see from equating the amount of energy that an object has to whatever the amount of whatever amount of energy it says it has. So we know that we have 1 joule because that's the kinetic energy. And how is kinetic energy defined? We have 1/2 mv squared. That's kinetic energy. It's that formula. We have this particular quantity. We know what this is. Since this is algebra, this is the only one we have left to solve for. So we have v squared is going to be equal to, if I multiply 2 on both sides, and that cancel. If I divide both sides by m, gets rid of them, puts it over here, and all we're left with is v squared. So I've got basically 2 joules divided by m. This also means that velocity is going to be equal to the square root of 2 joules divided by the mass. The mass in this particular case, they went easy on us and made it 1 kilogram. So this is going to be 2 joules divided by 1 kilogram. And when you do that, if you, let's say, go here, it won't let me do it. Okay. Fire up the oldie calculator. So if I take 2 and I take the square root of that, I end up with 1.4. So the velocity in this particular case and again, how do I know that this is meters per second? I know it because a joule is equal to 1 Newton meter. And I know that a Newton is the same as 1 kilogram meter per second squared. When that gets multiplied by this other unit over here, I get this. So when I divide it by the mass, the kilogram canceled, and I'm left with meters squared over seconds squared. So that's how I know what the velocity is. Now, am I correct? There we go. There we go. Okay. All right. So now let's, we've gone through problems 1 through 3 here. So let's go down a little bit further. Okay, next, water has a density of 1 gram per cubic centimeter. Express this density in units of kilogram per meters cubed. So I know here that water, let's say, one gram per meter. Now, I want to get rid of this and replace it with kilograms. In order for me to do that, again, I'll go through the dimensional analysis here. I know that there are 1,000 grams in 1 kilogram. I need to get rid of this. So I know that 100 centimeters I think I may be running up against, let's see if I can figure out. Oops. That is in fact not what I meant to do. Not interested in. Let's go back. Okay. All right. So give me a little white space up here. What is the density of this? Express it in those units. I think I have to go a little slower than what I was going. Okay. Now, let's try. Yeah, I got a little bit more room here. Now, I need to be able to get rid of centimeters cubed, and all I've got here is centimeters, so I need to cube this relation. Once I do that, then I'll end up with the proper units down here. So the kilogram or the gram cancels here. That cancels with this. So what am I left with? I'm left with 100 cubed. So that's 100 times 100 times 1. It's kilograms over 1,000. It's meters cubed. So 100, let's see, 1, 2, 3, 4, 5, 6. That gives me 6 zeros up on top. Okay. Why did it go blank? So I should have 1,000,000 up there. Okay, cancel that. So takes care of all of that. So I've got 1,000 or 1,000,000. So that should mean that I end up with 1,000 over 1 kilogram per meter. Is that in fact what I end up with? Let's see here. Oops. Boy. When the system wants to revolt, it's going to revolt. There we go. Indeed, that's what it is. 1 times 10 to the third kilograms per meters cubed. So that's indeed what I got. Now let's go back here. Okay, let's go back down here. Clear all of that out. Good. Now, let's okay. All right. Okay. Let's try number 5 here. Current of 0.01 milliamps is equal to how many microamps? Well, again, this is going to be one of those things where we just go through and we do the conversion. So I go here. So we start off here with 0.01 milliamps. And what we want to be able to do is to convert that. So the question is, how do we do that? Well, we know, and again, I'm going to kind of go back and forth here. How many milliamps do we have here in a microamp? How do we convert between the two? Well, if we go back here and let's charge up the old palette here. Oh, okay, so we know that when it comes to the microamps, that's what we want. So we know 10 to the minus third milliamps. And then we know we're going to have the microamps up the top. So the question is, how many of these microamps are there in milliamps? Well, as it turns out, the difference between the two is going to be that in one microamp, or I'm sorry, 1 milliamp, turns out that we're going to have 1,000 microamps. And the reason is that if we took 1 milliamp, this is going to be 1/1000th of what's going on here. If we took, we know that if we were to take this conversion of milliamps, or if we were to take, say, what is that? I'm trying to think of here. 1 amp, start with that, is equal to 10 to the third microamps. Because a milliamp is going to be taking whatever the basic unit is, and it's going to be dividing it into 1,000 parts. We also know that when it comes to microamps, it's going to be the same thing as saying 10 10 to the 6 microamps, because we know that's when you take it, you're basically dividing it into a million pieces. So if we were to take just this portion of it and basically divide both sides by 10 to the third, we would end up with just 1 milliamp. is equal to 10 to the third microamps. And that is the same conversion that we've got going on up here. So we have 0.01 milliamps being multiplied, and again, that is canceling with us, so I really should cancel that out, and that's being multiplied by 1,000 microamps. So that's 1, 2, 3. We should end up with 10 microamps. And is this in fact what the answer reflects here? Sure is. Okay, so we got that one knocked out. All right, so we're going to go on here and we're going to take a look at question 6. And so we've got a carbon nucleus, has a charge of plus 6e. It is accelerated from rest through a potential difference of 2,000 volts. So calculate the final kinetic energy in terms of keV. Now, I've got this over here, and let's go and let's look this up. It should be in the electricity and magnetism section. Probably not. Let's see. Okay, this will be a very important number going forward. Well, potential difference, that's what I needed. The electron. Actually, that's what I needed right there. Okay, so here we are, we're looking at change in energy is equal to W, which is equal to Q times V. Now, depending on what sort of unit you're looking at, this was volts. Again, we're probably looking at something here that's much smaller than that, which is going to be the electron volt. So, and that's what we're going to be looking at here is, you know, we're accelerating something through a certain voltage. We need to know what the charge is. And if we're looking at putting something in electron volts, essentially what we're doing is we're going to end up taking the charge and we're going to multiply it by the number of volts. So let's go back to the problem at hand. We're going to have a carbon nucleus of a charge of 0.6. We've got a potential difference of 2,000 volts. So multiplying the two, we should end up with the correct answer of, as soon as I can get 6e multiplied by 2,000 volts, electron volts. Work with me here. There we go. I think what happens sometimes is that it gets a little confused. Should be electron volts. Now let's see if we're right on 6e. And it says 12 keV. We have 12,000 electron volts. So what do we need to do to change that? Well, we're changing this 12,000 from, we know there's going to be 1 keV system gets really, really finicky. So we do this basically divided by 1,000 and we end up with 12 keV. That's our answer, at least for part A. Now, part B, repeat this for an alpha particle. Well, you can probably see here, this is going to end up being the same type of thing. We're going to end up with uh, 4E, because that is the charge. And that's going to get multiplied by, again, 2,000, say 1,000 volts or 2,000 volts. Oh, wait, I'm sorry, 4E, that's not right. The reason that is not right is because the charge is actually 2E on an alpha particle, so that's my bad. And we're going to multiply that by 2,000 volts. So we end up with 4,000 electron volts. Or when you do the conversion, you end up with 4 keV. So that's where that answer comes from. Basically, it's the charge multiplied. It's just much easier to do this. It's the charge multiplied by the volts that you're going through. Okay, so now let's go to 7. We have an alpha particle of mass of this that is accelerated from rest through a potential difference of 10,000 volts. Calculate the final kinetic energy in electron volts and the final speed of the particle. So again, an alpha particle accelerated through 10,000 volts is going to be the same as saying I really wish this thing would not do that. I don't know why it's picking up that it thinks it has to focus in on a certain point. Again, we're going to take 2 and we're going to multiply it by 10,000. And so we come up with 20,000 electron volts, or 20 keV. Is this in fact the answer for 7A? Let's see. 2000 EeV. Very good. Now, okay. So the next part is calculate the final kinetic energy and the final speed of the particle. Well, this is going to be a little bit more complex. Let's see if I can really like to have a little more room here. Let's see. Okay, it's not the collapse I was hoping for here. Let's see if maybe this will do it. There we go. A little bit of margin there. All right. So now let's go down here. All right, so what is the final kinetic energy in electron volts? We knew what that is. What is the final speed of this particle in meters per second? Now, we know that we have 20,000 electron volts. Unfortunately, electron volts doesn't immediately give us the ability to convert straight away into meters per second. So we're going to have to figure out how many joules this happens to be. How do we convert electron volts into joules? Well, Let's take a look here. I don't know why it's not taking the focus here. It should. Okay. So let's see if I guess it's okay. Go straight to magnetism, which is not what we need. Okay. Here's our conversion. 1 EV is equal to 1.6 times 10 to the minus 19th joules. So that's what we're going to need. So let's go back to the problem. Try to remember that 1.6 times 10 to the minus 19th joules. So we know here, if we go to the annotation, we go there, 1 EV is equal to 1.6 times joules. Okay. So now we're going to take this number of EVs and we're going to multiply it by some factor. We know that this is the number of EVs. So we need to take 1 EV multiplied by 1.6 times 10 to the minus 19th. Joules. So what does that end up being? Well, that and that cancel. So if I take let's clear this out. So I take 1.6, which is not helping, 1.6 times 10 raised to the minus 19th. Gives me that. I'm going to multiply that by 20,000. And this is what I end up with, 3.2, 1, 2, 3. I really wish this would put it scientific notation. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I end up with 3.2 times 10 to the minus 15th joules. Okay. Now, I know that this amount of energy, this is the kinetic energy. And again, just like the other problem that we had before, one half m v squared. So I know that in this case, v squared is going to be equal to 2 times 3.2 times 10. I love this system. It's 15th. All divided by the mass. So it'll be the square root of that, whatever that answer happens to be. And so let's find out what that is. Okay, so take that, multiply it by 2, and divide that by 6.64 times 10 raised to the minus 27th. Okay, I think I got a bad answer here. You know what? Let's go to Excel. Why are you? Okay. Okay. Don't really need this here. I just kind of, okay. I think the system is do what I need to do. So equals, what did I say? 3.2 times 10 raised to the 10 raised to the minus 15th. Yes, that would be fine. Equals 2 times this cell. And then the denominator here is going to be the 6.64 times 10 raised. Okay, when I say 10, I mean 10 raised to the minus 27th. That's going to be equal to that divided by this. And then I'm going to take the square root of this. And so I come up with 981,761. Now, indeed, is this what we have? Okay, oops, sorry. Let's go back to 981. Yep, that's it. 9.82 times 10 to the 5th. Because if I write out the answer that I found, it was 980 something or other. Okay, it's not letting me do that. It's because this is engaged. Okay. 981,761. So that's where it comes from. So 981,761. Meters per second. If you take that and you convert that into meters per second, or you want to write it in scientific notation, you go 1, 2, 3, 4, 5. So the velocity ends up being 9.8, and then you round times 10 to the 5th. Meters per second. Okay, so that's the answer to 7A, at least the second part of that. Okay, let's take that out. All right, repeat part A for the electron. Basically, you're going to be going through the same thing. What you're going to be doing here is changing out, I mean, when you take, when you find the number of electron volts, again, your charge here is going to be for the electron, so it's just going to be 1. One electron times, and in this case, again, it's 10,000 volts. And that should be what we have. Over here. So let's go down here. Let's pull this down a little bit. Yeah, and indeed, if you look at 7b, that's exactly what it is. So we go up here. We're going to go through the same thing here to try to figure out what the velocity is. So we're going to have to convert this over to so we know that 1 EV is the same as 1.6 times 10. This is really great when it works. 10 to the minus 19th. Obviously doesn't work that often. Minus 19th joules. Okay, so we do the conversion there. I'm going to go ahead and do this in Excel. Well, I'll tell you what, before we do that in Excel, whatever this conversion happens to be, which is 10,000 EV times the conversion factor, is going to end up equaling 1/2 m v squared. Solving is going to give v squared is equal to 2 times this mass divided by the mass, and then the velocity is going to end up being the square root of that. So now I'm going to take this over to here. So let's say over here, let's see, I had 3.2 times 10 to the 5th. So let's try to figure out 10,000 multiplied by 1.6 times 10 raised to the minus 19th. So I take that, multiply it by 2, and this should end up being not that, but 9.11 times 10 to the minus 31. So divide that by the other, and then take the square root. So I get 389,26759. Is that close to the answer? 5.93 times 10 to the 7th. Indeed, that is what we have. So this ends up being 5.93 times 10 to the 7th. Now, the final question here, part C, is going to be, is the neglect of special relativity justifiable in part A and in part B? And why? The reason they come back and they answer these questions of, is it reasonable to ignore it here? And that is because this is well less than 10% of the speed of light. When you start getting up above 10%, that's when you really need to start including calculations for relativity. And that's what it's trying to say here, is that the speed of the second particle right here, you're getting in above 10%. So you might want to consider making calculation. You might want to start factoring that in. So that's what that's referring to. So now let me go here and let me kind of clean up a little bit. Oops. Okay. So part 8, or problem 8, calculate the rest mass, energy, and MeV of a proton of 1.67 times 10 to the minus 27th. So as you can see there, the answer is 940 MeV. The question is, how do we get there? Well, here's how we get there. If you will go, and if you will look, as soon as it loads up, eventually. Okay. Let's go here and let's see if we can find special theory of relativity. Here we go. This famous equation right there. That's what we're going to end up needing. So E is equal to mc squared. I've heard it all your life, but this is actually what it means. So we're going to calculate the rest mass energy of a proton. So what do we need to do? Well, let's see. The first thing that we need to do is I'm going to write down the formula. So I'm going to say so we know what the speed of light squared is. We know what the mass of the proton is, and that will give us the energy. Okay, Sparky. When technology works, it's really great. When it doesn't, all right, so I'm going to take 1.67 times 10 raised to the minus 27th kilograms. I don't know why it keeps losing the focus like that. That's insane. And the speed of light in round figures is going to be that. So again, I'm going to go to Excel. Try to multiply this out. Okay, why is it doing this? Okay. Equals 1.67 times 10 raised to the minus 27 equals 3 times 10 raised to the 8th. So I am going to take this and multiply it by this quantity squared. And so that's what I come up with. 1.503 times 10 to the minus 10 joules. So I'm going to go back. Okay. So now the question is that we need to find out what that is in MeV. How do we convert? Well, again, if you'll remember, 1 EV is equal to 1.6 times 10 to the minus 19th joules. So to find the energy, at least in EV, I'm going to take 1.6 times 10. Whoops, sorry. Erase. I'm going to take 1.503 times 10 to the minus 10th joules. And I'm going to multiply. I ran out of room there, otherwise I'd write it next to it. I want to convert the joules into EV. So 1.6 times 10 to the minus 19th. Why do you hurt me? Okay. Boy. Okay. So what does that equal to? Well, go back to Excel. Can't do that because I don't have the focus here. Okay. Equals 1.503 times 10 raised to the minus 10th. On the bottom, or I'm going to take, let's see, I'm going to take 1.6 times 10 raised to the minus 19th. So I'm going to take this and I'm going to divide it by that. And I come up with 939,375,000. So if I go back, 939,375, okay. That's how many EV I have. To change that to MEV, I basically take it and divide it by a million because there's a million MEV in, or there's a million EV in one MEV. That means I end up with 940. Again, I take that and divide it by a million and round, and that's what I come up with. It's 940. So what is the ratio of the mass of a proton to an electron? Well, you can take the mass of the proton here, you can divide it by the electron mass here, and you'll come up with your answer. So I believe if we go to here, so we'll take the mass of the proton, which happens to be this, divided by the mass of the electron, which just happens to be this, and you come up with about 1800. Is that in fact what they have as the answer? At 1830. What did I come up with? 1833. There we go. Okay. let's take a crack at 9, and then I'm going to put the others into their own separate video. So for 9, a charge of 10 nanocoulombs is collected from an ion chamber that is irradiated in a linear accelerator beam. To how many electrons does this charge correspond? Well, here I'm going to have 10 nanocoulombs. Question is, when I say a coulomb, how does that translate to electrons? Well, let's kill that and let's go here. And let's kind of circle back. And let's see, it may not be here. I think it may be. Let's see, it may not be magnetism. Let's go back to the electron volt. I believe it's there. There we go. I thought I had it. No, I think it's further back. Actually, let's go to a charge and the Coulomb force. That's where it should be. There we go. That's what I need right there. So 1 electron charge is equal to this. So if I scroll a little bit, let's go back to here and let's say 10 nanocoulombs. I'm going to take that and I'm going to convert it. So I'm going to end up with, I know that 1 E is going to be equal to 1.6 times 10 to the minus 19th coulombs. Now the problem is that I have nanocoulombs here, and let me put that in as a dot. That way nobody gets confused. So that's going to be, those two are going to be multiplied together. How many coulombs do I actually have here? Well, nano means this gets multiplied by 10 to the 9th. So basically, this is going to be 1 times 10 to the 8th, 10 to the minus 8th. Coulombs. So I'm going to take 1 times 10 and I'm going to divide that by 1 point. I really wish it would not do that. And so the coulombs here are going to cancel actually, and I should be left with the number of electrons that I have. So if I go, oh, whoops, cancel that, go over to Excel. So I'm going to take 1 times 10 raised to the minus 8th. And on the bottom, 1.6 times 10 raised to the minus 19th, which is not the same as 29, equals this divided by that. So I end up with 625. So I've got 1, 2, 3, 4, 5. Hard to count the number of zeros there. 1, 2, 3, 4, 5, 6. 7, 8, 9, So it looks like 62.9. Yep, 6.3 times 10 to the 10th. So again, if I go back here, I take that, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I move that decimal point over here. I get 6 point, essentially 6. Times 10 to the 10th electrons. So that's what I've got here. Now let's take a look at part B. If the 10 nanocoulombs is collected over 1 minute, what is the current in terms of nanoamps? So if you go back here and you take a look at the discussion that they have regarding current, which is here 2.3.3. It's there, it's just not flipping over. You will notice that the current, or amps, is going to be coulombs per second. So that being said, if you go back here and you take, and I'm going to go ahead and clear out some of this stuff. So you go here and you take, is this not working? Okay. So you take the 10 nanocoulombs and you divide that by 1 minute, which is essentially the same thing as 60 seconds. Again, you can do the conversion here. 1 minute. And take that 1 minute. That's not going to work. Okay. 1 minute and divided by 60 seconds. That's where that comes from. So that goes there. So basically you end up with 0.17 coulombs per second, or 0.17. In this case, I should put nanocoulombs. And this would be nanoamps. And if I go here, kill this off, go here, you can see that's exactly what we've got there. Okay, so this is problems 1 through 9. In a separate video, I will go through the rest of them. That way the videos aren't quite that long.